In this lecture, we would like to understand a very important mechanism, which is the hidden Markov model. We introduced this in the last lecture, and we said that this is a very powerful tool for statistical natural language processing. We mentioned that part of speech tagging, which comes very early in the processing of textual data, has to use statistical techniques, and there the part of speech tags are learned by training from corpus data. Now, the machine which is typically used for this purpose is called the hidden Markov model, and we would like to devote our attention to this particular model. All right. So, as we mentioned last time that natural language processing happens at many layers. Many intelligence tasks are actually sequence leveling tasks, and these tasks are carried out in layers. Okay. So, tasks themselves are sequence leveling tasks, and they happen in layers. Within a layer, there are limited windows of information, and this naturally calls for strategies for dealing with uncertainty. The moment the information becomes limited, we know that we do not have all information to make a decision, and therefore, we must be resilient to uncertainty. We must have strategies for dealing with them. Probability and Markov processes give a way of dealing with uncertainty. Now, the example that was introduced and which we could look at in closer detail to understand this business of information processing in layers and information processing in a limited window within a layer. So, the sentence we have in front of us is, I went with my friend to the bank to withdraw some money, but was disappointed to find it closed. So, the first level of processing that happens is the part of speech tagging. The word syntactic categories, grammatical categories are first of all deciphered. So, from our discussion of part of speech tagging, we know that I is a pronoun, went is a verb, with is a preposition, my is a possessive pronoun, friend is a noun, to is a preposition, the is an article. The first difficulty we meet with is in the word bank. Bank can be a verb, meaning thereby depend. I bank on my friends for their support in case of distress, or bank could be a noun, a river bank or a bank where we deposit money or we withdraw money from. To is a preposition. Withdraw once again is problematic because it can have noun and verb categories. Almost all nouns in English can be used as verbs, and many verbs can be used as nouns. Some is an adjective, it is a quantifier. Money is a noun, comma is comma, but it is a conjunction. Was is an auxiliary verb. Disappointed can be both an adjective and a verb. In this case, it is a verb, but one could say, for example, the disappointed crowd, the disappointed spectators, where this is acting like an adjective. To is preposition. Find can be both noun and verb. I would like to find my key, here it is a verb. This new player is a terrific find, which means it is a noun. It is a pronoun. Closed can be an adjective or a verb. Here it is closed, the bank is closed, but you could have the closed bank for example, and there closed is an adjective. So, we see that when we process the sentence on our road to the meaning, we do find that we have to disambiguate categories of the words. So, here is the first layer, the part of speech layer. One or two examples of this are given. Bank can be noun or verb, closed can be verb or adjective. Similarly, find can be noun or verb. Then we see the next layer, which is the sense disambiguation layer. So, if you go left to right once again, I is a pronoun, no sense ambiguity. Went can be very ambiguous. Go is a verb with many meanings. Go has more than 50 meanings in English language. Okay. And went is the past tense form, at least part of speech disambiguation does not apply here, because nouns do not undergo morphological transformation in tense, but went can have many different senses depending on the senses of go. Okay. So, for example, go with the motions. Go with the motions means to conform with the tradition. Okay. Go home, this is the act of going, act of moving home, moving to home. Then there are many other meanings. So, go is ambiguous. Bank we know is a classic example of ambiguity, because it can be river bank or the financial bank. Withdraw can mean to take away or go away. Similarly, there is a pronoun drop at this place, but I was disappointed. So, I has to be put in here, but from here, from the discourse segment which came before, and there are many nouns and pronouns, I, friend, bank, money. These are candidate nouns, but some of them will have type mismatch. For example, money and bank cannot be disappointed. So, we should have an animate entity here. Then I and friend are the candidates, I is resolved. So, this is the pronoun drop resolve. Scope ambiguity is that with is a preposition, and what is the scope of with? With can form a preposition phrase, but how much of text does it demand to form the preposition phrase? So, here with my friend, but if it was with my friend from America, then the whole thing becomes the preposition phrase, with my friend from America. So, the preposition phrase has to stop with friend. So, this is a disambiguation task, because you have to decide on the amount of text to eat up to form the phrase. Then the other difficulty, the final difficulty, is co-referencing, where it, this pronoun, has to be bound to a particular noun. So, what was closed was bank. So, it has to be bound to bank, but how does the system know? How does the machine know this? It will have to search amongst the possible nouns in the previous clause. So, all these are different layers of information processing or disambiguation task, and they necessarily work with a limited amount of information at any level. The information is limited, and therefore, there is uncertainty, and we need a machine to deal with uncertainty. So, the answer to that is often a very elegant machine, the hidden Markov model. So, we proceed to describe this model with its mathematical machinery and description and definition. But before that, we have a motivating example which is found in most texts and papers on HMM. The setting is as follows. There are 3 containers, 3 urns, urn 1, urn 2 and urn 3, and there are totally 300 balls distributed amongst these urns with 100 balls each in one urn. So, urn 1 contains 100 balls, 2 contains 100 balls, 3 contains 100 balls. And these 100 balls again are of different colors. For example, in urn 1, we have 30 red balls, 50 green balls and 20 blue balls. Similarly, in urn 2, 10 red balls, 40 green balls, 50 blue balls. In urn 3, 60 red, 10 green and 30 blue balls. You can see that if you sum these numbers horizontally. So, red 30, red 10 and red 60, that means the total number of red balls is 100, which are distributed amongst the 3 urns. Similarly, the proportion of green balls, or the total number of green balls, is also 100, distributed as 50, 40 and 10 in the 3 urns respectively. Blue balls are also 100 in number, distributed as 20 in first urn, 50 in urn 2 and 30 in arm 3. So, this is the situation, and a person picks up balls from the arms and places them one after the other, and the color of the ball is recorded. There is a probability associated with the urn pickup itself. Which urn the ball should come from is also probabilistically decided. And what is known is that we know the transition probability of going from one urn to another. So, for example, if we look at this row and the corresponding column values, we see that from urn 1 you can go to urn 1 again with probability of 0.1. That means, if a person has drawn a ball from urn 1, the probability of him drawing the ball again from urn 1 is 0.1. Similarly, the probability of drawing from urn 2 after the ball was drawn from urn 1 is 0.4. The probability of drawing from urn 3 after having drawn the ball from urn 1 is 0.5. So, a row gives the next urn after a particular urn, and a column gives the previous urns for a given urn. Okay, so, this is the transition probability table. The other probability is the observation probability table. So, for urn 1, the probability of drawing a red ball is 0.3, that of green ball is 0.5, that of blue ball is 0.2. And the reason for this is that the 30% of balls in urn 1 are red, 50% are green, 20% are blue. Okay. So, the probability is this 0.3, 0.5 and 0.2. Now, the question that is asked is, here is the observation of the colors of the balls drawn R, R, G, G, B, R, G, R, that is red, red, green, green, blue, red, green, red. Then from this observation sequence, can we identify the state sequence? That means, the urns which were chosen corresponding to each ball. So, this is not easily computable, we have to predict this. Now, we make some remarks. So, when we are discussing this problem, what we are saying is that the state has to be predicted corresponding to the observation. So, we have the observation sequence O, and we have to predict the states, which is the state sequence. The notation is O the observation sequence, S the state sequence. Now, the point being made is that many problems in AI are of this kind, fall into this class. Predict hidden from observed. So, this is the state of affairs. We have observation sequence, we have to predict the hidden sequence. Many problems in AI fall into this category. For example, in machine learning, in natural language processing, in planning, we will in particular concentrate on natural language processing. So, let me just illustrate this point. The point is that in part of speech tagging, which we have understood to an extent, and we have also looked at the derivations. In part of speech tagging, we have the words, okay, the man laughs in a sentence. Now, the part of speech for the is dt, the determiner. The part of speech for man is noun, and the part of speech for laughs is verb. Okay. So, determiner, noun and verb. Now, we have the sequence of words, the, man and laughs. The sequence labeling task is to produce part of speeches dt, nn and vbs. So, as if the observations are our words, this is O1, O2 and O3, and we have to predict what is hidden below this. What is hidden below this is T1, the tag 1, T2 and T3. Okay. So, the problem that comes in front of us now is that of predicting a state sequence from the observation sequence. The state sequence in this case is the tag sequence, and the observation sequence is the word sequence. All right. Now, this is slightly unintuitive to a person. This may be looked upon as slightly unintuitive. The reason is that when you have these arms, we look at the transparency. When we look at when we see the arms, then arms can be looked upon as states, because arms are producing balls, okay, different colors balls. In what way can we say that the word sequence is produced by the tag sequence? Okay. How can we stretch this example to the example of language processing, where the problem is to produce tag sequence for the word sequence? Okay. The labeling task is to produce the tags. So, isn't it somewhat unintuitive to think that there is a hidden sequence of states in the form of tags and the observations are words? Well, the best that can be said at this stage is that this is a convenient formulation for being able to apply a powerful tool named the hidden Markov model for the problem of part of speech tagging. It may seem unintuitive that the state sequence or the tag sequence is producing the observation sequence, which is the words. A more common thing to think is to think that the word sequence is producing the tags. Okay. But that is a different approach of solving the same problem. We will see that later. Now, in this case, it is convenient for us to think of the tag sequence generating the word sequence. So, this is a generative way of solving the part of speech tagging problem. We will look at the debate of discriminative versus generative model. All right. So, this is what we have written. The state sequence is the tag sequence T, observation sequence is O, the word sequence, and we have seen the deduction for this as to how the tag sequence can be found out. Let us discuss the theory of HMM in more detail. All right. So, we have got these observation probabilities, the transition probabilities, the observation sequence in the form of the colors of balls are given. The balls are of course drawn with replacement. Okay. Now, the question is, what is the state sequence or the arm sequence? From the transition table and the observation table, we can draw a machine here with transition probabilities and the output probabilities. Okay. So, we see here that arm 1, the probability of coming back to arm 1 immediately after arm 1 is 0.1, and the probability of drawing red, green and blue balls is given as 0.3, 0.5 and 0.2 respectively. Similarly, for arm 2, the probability of coming back to arm 2 is 0.2, red, green and blue ball probabilities are given here of drawing them. Similarly, for arm 3. These arrows here, which are straight lines, they indicate the transition probability. So, from U 1 we can go to U 2 with probability 0.4. So, this was given in the transition probability table. From U 2 I can go to U 3 with transition probability of 0.2 and so on. Okay. So, this is a convenient and very clear representation which embeds or combines both the output probability of drawing these balls and the transition probability. It turns out that we will not need so many arrows after all, because we can combine the transition and output probabilities, and we can have a more compact machine as shown here. So, for every state we have transitions from the state into another state, okay, and the output probabilities are absorbed in the state transitions. In what way? In this way, that the red ball R is shown here with comma and then this number 0.03. What is this? This is the probability that U1 will go back to U1 and will produce a red ball. Okay. So, this is a joint event. Okay. It is a joint probability. This R here with 0.03 has the following meaning. So, this is a machine which combines both transition and output probabilities, and we would like to see how it comes about, but first of all let me write down the meaning of this probability R comma 0.03 with an arc here and the state here. The meaning is this, that we have U1 here and U1 is coming back to U1 with R comma 0.03. The meaning of this diagram is that U1 goes to state U1, that is a ball is drawn from U1 after U1 and this is a joint probability and the ball is red. Okay. So, this is the meaning. The meaning is that we draw a ball again from U1, but before that we have produced a red ball R from U1. So, this is a probability of a composite event. The composite event is U1 goes to U1, okay, and the ball drawn is red. All right. So, the slide shows other numbers also. So, we pick up another quantity, let us say, suppose I take this particular quantity g comma 0.08 adjacent to this particular arrow, g comma 0.08 adjacent to this arrow. The arrow direction is from U2 to U3, the level is g, that is green ball, and the probability is 0.08. So, what it all means is that the probability of producing a green ball from U2 and then going to arm U3 is 0.08. So, we produce a green ball from arm 2 and the next arm to choose is arm 3. All right. So, this is a composite event, the probability of going from U2 to U3 and producing a G from U2. So, this is a more compact representation compared to the previous representation, where the outgoing arcs were representing ball drawing probabilities and the state to state arcs were depicting the transition probabilities. So, this is the state sequence here, this is the state set U1, U2 and U3. The observation sequence is from the set R, G and B. So, observations are written as O1 to On and state sequence is Q1 to Qn. There is an initial probability associated with the states. What is the probability that we draw a ball first? Okay, that is why pi. We draw a ball first from arm 1. What is the probability that we first draw a ball from arm 2? Probability we first draw a ball from arm 3 and so on. And then this A is the transition probability table, B is the observation probability table. So, the observations and states can be depicted in this way. We have the observations R R, G G, B R, G R. These observations are O1, O2, O3 up to O8 and the states corresponding to these are S1, S2, S3 up to S8. Okay. So, each state is producing a particular color of the ball, a particular observation. Now, what are these S's? Each SI is a particular state and it can take values U1, U2 or U3. Okay, that means one of the 3 arms. SI is a particular state, but S whole thing is a state sequence. O is an observation sequence, in this case it is these R R G G, B R G R. We are interested in S star, the best possible state or arm sequence. Our goal is to maximize P S given O by choosing the best S, and S star is the best possible state sequence. All right. So, maximizing probability value for a particular value of the independent variable, this is captured by the argmax function. So, this is expressed here S star, the best possible state sequence, is equal to argmax over all possible S, where the argmax happens over this expression P S given O. That means, we vary S and O is the observation sequence which is given. So, we vary S and we obtain different values of this probability value P S given O. Wherever we reach a maximum of P S given O, we record that particular S and the output is given as that particular S, which is S star. So, this is the best S possible for us, because for that S the probability P S given O is maximized. Now, here is a false start possibility in the mathematical treatment of the situation, where we find that given the observation sequence, our interest is in the best possible state sequence. So, suppose we mathematically treat this expression P S given O. Now, P S given O is nothing but P S 1 to 8 given O 1 to O 8. So, this is a convenient notation which shows the state sequence S 1, S 2 up to S 8 and is written in a shorthand 1 to 8. Similarly, the observation sequence O 1, O 2, O 3 up to O 8 written in a shorthand fashion O 1 dash 8. So, by applying chain rule, we obtain P S given O as P S 1, the first state S 1 given O, into P S 2 given S 1 comma O, where S 1 becomes the conditioning variable, then P S 3 given S 1 and S 2, which is written as S 1 dash 2 and O, and lastly P S 8 given S 1 to 7 and O. So, S 1 to 7 should be understood to mean S 1, S 2, S 3 up to S 7. Okay. So, this is the way the whole probability is broken down into a set of probability values whose product is taken. Now, we invoke the Markov assumption. What do we do? The Markov assumption states that any set, any state actually depends only on the previous state. So, from this expression, for example, P S 3 given S 1, S 2 and O, we can drop S 1, because S 1 is not the immediately preceding state. So, P S 3 given S 1, S 2 and O will become P S 3 given S 2 and O. And here we have P S 8 given S 7 and O, all the previous states from S 1 to S 6 are ignored. So, this is a Markov's assumption, a state depends only on the previous state, and what is happening here is that we are making an assumption of Markov state for order k equal to 1. Okay. So, this is order 1 Markov assumption, that means only one previous state matters. Similarly, we could have order 2 Markov assumption, where a state would depend on previous 2 states. Now, the problem is, when you have treated the expression mathematically this way, we find that we have these probability values P S 1 given O, P S 2 given S 1 and O, P S 3 given S 2 and O, and so on, but these probability values cannot be computed easily. Okay. These parameters are not obtainable easily, they are cumbersome items which need to be processed further. Instead of that, we can make use of another very nice theorem called the Bayes theorem, which along with Markov assumption is a very powerful theoretical construct. Okay. Bayes theorem states that P A given B, where A and B are random variables, P A given B is equal to P A into P B given A divided by P B. So, this is the way a probability value is turned around, P A B, P B A, but it is multiplied by P A and divided by P B. So, P A is called the prior probability, P B given A is called the likelihood. Now, when we take argmax over S of P S given O, we can equivalently make the expression as argmax over S of P s into P o given S. All right. It is not difficult to see that the denominator P o can be ignored, because it is independent of S and it comes as a constant factor for all these expressions, P s into P o given S divided by P o. So, P o is independent of S and therefore, it can be eliminated from consideration. So, this is Bayes theorem and it is a very powerful construct. So, let me make some remark here and write it down in the form of a list of things. So, we are saying that Bayes theorem is invoked along with Markov assumption. So, a very powerful tool for problem solving in statistical AI, which means machine learning, NLP, planning and so on. A very powerful tool for problem solving in statistical AI is the combination Markov assumption plus naive Bayes. Okay. So, this becomes a very powerful tool for solving many different problems in AI. Markov assumption plus naive Bayes. Naive Bayes is utilized through the Bayes theorem. Markov assumption is invoked through the dependence of states on previous states. Okay. So, let us remember this Markov assumption plus naive Bayes. So, after invoking the Bayes theorem, now we find that state transition probability, the prior, which is P s, can be treated in the following way. P s is nothing but P of s from 1 to 8. So, this is actually a sequence P of S 1, S 2, S 3 up to S 8, and this can be written as P S 1 into P S 2 given S 1, P S 3 given S 1 and S 2, P S 4 given S 1, S 2, S 3 and so on. The final probability is P S 8 given S 1, S 2 up to S 7. Now, by Markov assumption of order 1, k is equal to 1, we can drop all those states which are not immediately preceding. So, then P s becomes equal to P s 1 into P s 2 given S 1, P s 3 given S 2, P s 4 given S 3 and so on until P s 8 given S 7. Okay. So, this is a an easy expression which can be computed by some means, which you have to see. So, the prior probability has become a product of this kind of bigram probabilities. Okay, we call them bigram probabilities. We have here two states S 1 and S 2 interacting with each other, S 3 and S 2 interacting with each other. In general, a state S k interacting with S k plus 1. So, we have treated the prior probability component. We come to the next probability component P o given S. So, P o given S can be written as P o 1 given S 1 to 8, P o 2 given A 1 O 1 and S 1 to 8, P o 3 given O 1 to 2 and the states S 1, S 2 up to S 8. Finally, the observation O 8, P O 8 given O 1 to O 7 and S 1 to S 8. So, now we invoke another assumption and this complicated expression gets simplified. We assume that a ball drawn depends only on the arm chosen, nothing else. This is a very reasonable assumption in the current situation, because when a ball is drawn with replacement from an arm, presumably there no other factor in the world influences the color of that ball drawn. It purely depends on the arm from where it is coming, because we have a probability associated with the color coming from an arm. So, when we make that assumption, we know that O 1 depends only on S 1, O 1 depends only on its current arm, O 2 depends on current which is current state S 2, O 3 depends on the current state S 3 and nothing else, and therefore, all these probability factors can be written as P O1 given S1 into P O2 given S2, P O3 given S3 and finally, P O8 given S8. So, once you have got all these expressions ready, we can see that the probability values come in the following way. P s given O is P s into P O given S, and this is equal to P s 1 into P s 2 given S 1, P s 3 given S 2 into P s 8 given S 1 S 7, and the probability values coming from the observations. So, P O 1 given S 1, P O 2 given S 2, finally, P O 8 given S 8. So, these probability values now can be grouped together. We will not worry about the first line and the last line. In between, we see that a grouping has been done. So, we have P O 1 given S 1 into P S 2 given S 1, P O 2 given S 2 and P S 3 given S 2, P O 3 given S 3 and P S 4 given S 3. So, in any such line, what is happening is that we have a state S k and the corresponding observation O k multiplied by the probability of the state and its next state. Okay, probability of the next state given the previous state. So, this is systematically done for all the lines until O 7. Okay. O 7 because S 7 is the corresponding state and the next state is also well defined S 8. So, this is shown in the picture here, where we have O 1, O 2 up to O 7 and we have different colored balls which are coming as observation sequence, and below that is the state sequence S 1 to S 8. This S 9 here is the final state. S 0 is introduced as a fictitious state. Okay. This is the state where no urn has been chosen and the drawing of balls has to begin. Okay. So, this is the state S 0, this is the start of the ball drawing situation, and here the observation is epsilon. Epsilon is an empty transition, which essentially means that nothing is done except that there is a state change from S 0 to S 1. Epsilon is the empty string. So, the meaning of this is that initially there is no red, green or blue ball produced. We go straight from initial state S 0 to one of the urns, as is expressed by the fact that each state can take a value u 1, u 2 or u 3. So, now O 0 given S 0, probability of O 0 given S 0. So, probability of epsilon transition given S 0, that is always 1. Okay. So, initially no ball will be drawn and we will go from a starting state to a state which corresponds to the urn, and similarly we will go from a state S 0 to S 1 positively. S 1 can be one of u 1, u 2 or u 3. This is probability, this is the probability which is saying that we will begin choosing urn after all. The last line is also important. We had P O 8 given S 8. Now, this is multiplied by P S 9 given S 8. Now, S 8 is the length of the observation sequence, S 8 is the last state corresponding to a ball drawn, and S 9 is the final state. So, P S 9 given S 8 is definitely going to be 1. Okay. Therefore, it does not disturb the equality when we introduce this term. So, we have taken the observation sequence, we have taken the state sequence, and we have done something useful here or something necessary here. We have introduced a final state and we have introduced an initial state with its observation, and the observation is epsilon. The purpose of doing this is that we want to capture the start of the process and we also want to capture the end of the process. Okay. That is one purpose. The next purpose is that we can combine the terms and we can introduce a useful notation. So, what we have seen last time in the last slide is that we have O k for a state S k and a transition Sk to Sk plus 1, we write this notation Pok given Sk into Sk plus given Sk as probability of Sk arrow Sk plus 1. The meaning of this arrow is that the next state after Sk is Sk plus 1 on the output or input to be OK. Okay. So, OK is the output and the state transition is from Sk to Sk plus 1. So, this is diagrammatically depicted here. We know that S0 is the starting state, there is an epsilon transition to S1, S1 goes to S2, S2 goes to S2 goes to S3, S3 goes to S4, S4 to S5 and so on. And everywhere the arc is marked with the observation. That means, S1 after producing R goes to S2. In other words, if S1 was one of the arms, let us say arm number 2 and suppose S2 is arm number 3. So, we go from arm number 2 to arm number 3 with the transition R, that means having drawn the red ball. So, you can see the immense utility and intuitiveness of this particular expression. This turns our probabilistic expression into actually a probabilistic finite state automaton. All right. So, this expression that we had produced of observation probability and state probability, and we group them together. So, P O0 given S0 into P S1 given S0, P O1 given S1 into P S2 given S1. Okay. So, these are the groups, and for each of them we have now a notation. For example, what will be the notation for this? The notation for is that this is a state S0 going to S1, S0 to S1 on the symbol O0. Okay. Similarly, this expression if we try, it goes from state S5 to S6 as is indicated by the conditional probability here, and the output produced is O5, okay, which is one of the colored balls. Therefore, this probabilistic expression P s into P o given S has now become a finite state machine with probabilities associated with the arcs and the observations also marked on the arcs. So, this expression has become a finite state machine. All right. So, this is a very useful notation. It is a very useful notation because the HMM after all is a finite state machine with probabilities on the arcs, and the probabilities on the arcs come from this theory which has been worked out in front of you. P OK given S k into P S5 P S5 given S4 which is equal to P S4 to S5 on the symbol O5. All right. So, this is the finite state machine depicting the situation here. Now, we would like to see if we can make use of this machine and compute the best probability value. So, this we will draw on the paper and show you the computation. For this, I need the probability values, I need this machine. So, our goal now is to get the probability value of this sequence P P R R G G B R G R. Okay. We want to get the probability of this sequence or the probability of the state sequence S given this observation sequence, and the best state probability is S star. This we would like to get, and this we can get from the automaton that we had got, which is S0, S1, then S1, S2, 1 R and so on, and finally, we have S8 going to S9 with observation R, and there are probability values associated with them. So, this corresponds to the following search configuration. If we do not have any restrictive influence and we produce the state sequence for this, which is u1, u2 or u3, then the number of possibilities are 3 into 3 into 3 8 times. So, the search space become 3 to the power 8, or the search space size would be the number of states to the power the length of the observation, states length of OBS. So, this is a tremendous amount of computation. We will see in the next class how to efficiently compute it by Viterbi algorithm.